reaction. I'll definitely give you guys the definition and then we'll take it from there, okay?
Okay.
So when we talk about the rate of reaction, we talk about the change in concentration of products or reactants per unit time. So you'll see that in most cases we will be referring to the change in concentration. So the rate of reaction, to define this, you're gonna tell them that the rate of reaction, this is the change in concentration. I hope you guys understand that part. When I say this is the change in concentration. Let me write that down. The change in concentration. Concentration, and then of what? Of products or of products or the reactants per unit time, right? So that is the rate of reaction per unit time. Okay, so now let's go back and read what is going on this statement. The statement says that we have two experiments, 1 and 2 are conducted to investigate one of the factors that affect the rate of reaction. Looking at this, we can see that now we are investigating the concentration, but don't worry, everything will make sense now. So the rate of reaction of aluminum carbonate, okay? So aluminum carbonate, we need to understand how one of the factors affect that with excess hydrochloric acid. The balance equation is given below and the apparatus used, those are the apparatus. Guys, even if you don't understand what is the statement saying or you don't have a clue, you still have a chance to win and collect all the marks. Look at how we're going to answer these questions. So the reaction conditions used for each experiment are as follows. So let's look at experiment 1. So the first experiment, we have the volume as 100 centimeter cube and the concentration as 1.5 mole per decimeter of what? Of hydrochloric acid. It reacts with the aluminum carbonate of 0.016. So this tells you that this is the initial number of moles, the initial number of moles of what? Of that aluminum carbonate. I hope you are happy with that. I hope you understand that, because it's very important that we note this is the initial. Initial means that what we start with. We're going to start with the 0.06. This is what we start with initially. And then on experiment 2, this is another experiment. We have 50 centimeter cube. This is the volume for the first experiment, and this is the volume for the second experiment. So the difference is that this one is 100, that one is 50. So you can see that the second one, the first one has the concentration of 1.5 mole per decimeter. This is the concentration. The concentration of hydrochloric acid is given as 1.5, but for this one is 2. So this tells you that experiment 2 has higher concentration than experiment 1. Guys, what I'm saying, it's obvious, it's there on the statement. We know that 1.5 it's less than 2. So the experiment 2 has a higher concentration. You understand? Are you guys still with me on that?
Yes, sir.
And you'll see, Emife, why you need to understand which one has the higher concentration. And then now it reacts with what? The same number of moles. So this one initially, even in experiment 2, initially we still start with the initial number of mole of what? Of that aluminum carbonate. I hope you guys are happy with that. So initially, in the first experiment and the second experiment, we start with the same number of moles, okay?
Yes, sir.
So now let's answer that 5.2 and see what we need to do on the 5.2. They say, using the experimental setup above, state the measurement that must be made to determine the rate of this reaction. So guys, it's easy. What is different there? Looking at experiment 1 and experiment 2, what is different? The volume. Can you see that? You can talk about the volume. So this tells you that we're going to measure the volume of the gas at a regular time intervals, or you can say the volume of gas. Okay? Because the question says that we need to, in order for us to conduct this, we need to measure the volume of the gas. So the first one that I'm going to give them is that we're going to measure the volume. You can just write the volume gas only, it's fine. So we're going to say the volume of the gas. And remember, this is rates of reaction. We know that another thing that we need to measure is the time. It's always measuring the time. How can we say this? The time taken for that aluminum carbonate to be used up in both reactions. We need to know which one will be completed fast. So you can give them the 2 and you'll definitely get that 2 marks. First thing, the volume of the gas, the time it will take that aluminum carbonate to be used up, the time for this guy to be used up. That's one thing we can measure. Then we go to 5.3. But before that, do you guys have any question on that 5.2?
No.
Okay.
Okay, what about 5.3? Use the collision theory to explain how the average reaction rate in experiment 1 differs from the average reaction rate in experiment 2. Guys, when you get this type of question, and this is 3 marks, you need to understand how the collision theory works. First thing first, tell us about the orientation, then you'll get 1 mark. Then number 2, let me write this down. Where can we put this? So what I'm saying is that I need you to tell us about the orientation. Né? So this is how the collision theory works. Right. So the collision theory, number 1, you're going to tell us about the orientation. Number 2, tell us about if you have a more effective collision. Okay. If this does not make sense, please just give me a second. You're gonna get this now, né? And then once you tell us about that, tell us about the reaction rate. Guys, it's always like this. Reaction rate. If you get this question wrong in an exam, trust me, we're going to, even when I give you an assignment, because I'll definitely give you an assignment to see if you are ready for exam. If you get this wrong, you see how I'm explaining this. First thing first, talk about the orientation. 1 mark. Tell us about the effective collision. 1 mark. The rate of reaction. Another mark. Then you'll definitely get that 3 marks. So now let's go back to the question. We're coming back to that part now. They want you to use the collision theory to explain how the average reaction rate in experiment 1 differs from the average rate in experiment 2. Guys, you don't have to have 2 blocks where you'll say in experiment 1 this, and then in experiment 2 this. No, focus on one experiment. Talk about that experiment. The marker knows that the other experiment will be the opposite of that. For example, let's say I choose experiment 2. You see, if I choose experiment 2 to answer this question, my focus will be on experiment 2. So on experiment 2, you look at that one factor that affects the rate of reaction. What is the factor that we are using now? The concentration. Okay? The concentration is the factor that we are using. So I'll focus on experiment 2, the concentration. So look at this. Experiment 2 has more concentration than experiment 1. So what I'm going to do is that since it's more, this tells you that the concentration of experiment 1 is less, and we have less of HCl, and then in experiment 2 we have more of HCl. I hope you understand that part. So that will be my first statement. I'll tell the marker that in experiment 2 there's more HCl because they said 50 centimeter of 2 mole per decimeter cube of HCl react with what? You understand? So that two concentration is for HCl. Then talk about that HCl. So I'm gonna write this down and say, let me write this down. First thing, I'm gonna tell the marker which experiment am I referring to. Now I'm gonna talk about experiment 2. So I'll say number 1, I'm going to talk about the orientation. I'll say that there's more HCl in experiment 2. Particles, there's more particles, right? So I think already you know if there's more particles, what will happen? There's more particles per unit volume. Okay, I said talk about the orientation. So this tells you that if there's more particle, what will happen? More particles means that there'll be more particles with correct orientation. With correct orientation. So now, Emita, do you want to tell me what will happen next if we have more particles with correct orientation? What can we say about the effective collision?
Sir?
Listen, we are saying that there's more particles per unit volume. So this tells us that there's more particle with correct orientation. So more of HCl with correct particle. So now, if there's more particle with the correct orientation, what will happen? What can you say about the effective collision?
It's going to be more effective.
Exactly. There'll be more effective. There'll be more effective collision per unit time. There'll be more effective collision per unit time. So now, if there's more collision per unit time, what can we say about the reaction rate? If there's more particle with correct orientation, more effective collision per unit time, therefore we can conclude and say the higher the reaction rate. Johan, it's the higher the reaction rate, guys. It's always like this. This is always the answer. First thing first, check about the concentration. Do you have high concentration or low concentration? High concentration, it makes the reaction to complete to be faster. So we're going to produce more products fast. So now you check the concentration. If we are talking about the concentration, we'll also talk about the large surface area in other lessons, but on this lesson, the main focus is the concentration. So if the exam talks about the concentration, you check. The one that has the more concentration will have more, we're going to talk about that concentration. We're going to say there's more HCl particles per unit time with correct orientation. So there'll be more effective collision per unit time, higher, the higher the reaction rate. I'm not sure how I can give you guys, how can I give you the example? Maybe one example. Which example can we use? Which more example? I just want to think of a silly example that you guys can relate to what is going on here. Okay, maybe the example that I can give you, Johan, are you listening?
Yes, sir.
I'm just gonna give you a silly example. I need you to take the cold water, and then I need Emisha to take the hot water. So we're just gonna do this silly example. So I have the cold water and the hot water. So now my water, the temperature of the water, it will be my reaction rate. Okay, so now where there's cold water, I'm gonna put my concentration, which will be sugar. Okay, which will be sugar, and I'll put a lot of sugar in both. It's fine. So let's say we put sugar in the coldest one and the hottest one. Which one will melt first? The one that is hot. You understand? Yeah. So the one that is hot, this tells you that it has effective collision per unit time, because there is a higher reaction rate, because the water has a higher temperature. This is what is going on here. Do you guys understand?
Yes, sir.
Okay, I just wanted to make that, even though the example is not related to what we are currently working on, I'm just
Sir,
trying to explain how this works. I'm listening.
can you explain the definition of effective collision, please?
Okay, so you know what we mean when we say effective collision, eh?
Mm.
Is the speed how things collide.
Mm.
Do you get what I'm trying to say?
Okay, so when we refer to this, we said that it's going to be more effective, meaning that it collides faster.
Exactly. There'll be more effective collision. It collides, but the particles will collide faster.
Okay.
Is that making sense?
Collides faster, then the reaction rate becomes higher.
Exactly.
Okay.
Did I
get it.
answer your question?
Yes.
Okay. Just give me a second. Okay, so you know now, looking at this, I just like the question that you asked when you say more. What is effective collision? Remember, let's say this that effective collision, it's between reactants particles that results in a chemical reaction. It will be between what? It will be between reactants. Okay.
Mm-hmm.
So now it requires particles to collide with sufficient kinetic energy.
Mm.
You understand? And when they collide, they must collide with the proper orientation to break old bonds and form new ones. I'm not sure if this makes sense. So that is what we are referring to when we say more effective collision.
Oh, okay. Okay.
You understand?
Yes, sir.
We are saying that an effective collision is a collision that happens between reactants and it results in a chemical reaction. So it needs those reactants, they must collide with sufficient kinetic energy. So and the proper orientation. Why? Because they need to break the old bonds and form new ones. So the new ones will be the product. You understand?
Mm.
So now there are requirements that needs for this effective collision. Number one, we need the minimum activation energy and the correct orientation. Always talk about those two. And then the outcome, it's what we call about the formation of products. And then nice. So if we increase the reaction, if we increase the rate, this tells you that we can increase the rate by increasing what? The temperature. Remember, I just gave you guys an example with the cold water and the hot water.
Mm.
Yeah, so we increase. So if you want to increase the rate, you need to increase the temperature. Why? Or the temperature, I'm referring to the higher energy. So you can also increase the concentration, and then you can also use a catalyst to lower what? To lower that activation energy. But don't worry, guys, we still have a lot of sessions to talk about this.
Okay, wait, sir. So, can sir
Yes.
please go back to the question? There's something I want to ask.
Okay.
So, here by experiment 1, right?
Uh-huh.
Is this the same experiment? It's like the same like concentration and whatever, but at the beginning. Or is this two different containers with
exactly two different containers, but they have different volumes, different concentration, but they all start with the same amount of aluminum carbonate. So we are investigating how concentration will affect the rate of these two reactions.
Oh, and then we increased concentration was increased here, therefore. Okay. Okay.
Emily, do you want us to talk about experiment 2?
No, I understand it now because I was confused with, okay, so we have different concentrations. Was it at the beginning, or is it two different things with two different values experiencing a different thing going on? But now,
Yeah, now you get it.
mhm,
So look at this. In experiment 1, there's less HCl particles
per unit.
per unit time.
Mm,
So therefore, this tells you that there will be less
effective collision.
effective. That is the one for the colloid, effective collision per unit time. And then this tells you that the reaction, the lower
Reaction rate.
the reaction rate. You understand? You just talk about the opposite of that.
Okay, I get it.
All good, ne?
Mm-hmm.
You still happy?
Yes, sir.
Okay, now on 5.4, if we look at 5.4, they say the average rate in experiment 2 during the first 2.5 minutes. So we are given the average rate. And when I have this, you know what I expect you guys to do? You always need to know these formulas, né? So to answer this question, first thing first, just know that the formula for the average rate, it's equals to the change in, let's say negative, the change in number of moles all over the change in time. Or you can say the change in number of moles over the change in time. So now the most thing that we need to ask yourself, when do we use the positive? When do we use the negative? When is this negative and when is this positive? So guys, listen, I will work on different examples now to calculate the guys. These are some of the questions you don't need the background theory, don't need anything. By understanding what we're going to explain now, you are good to go. Look at this. The one that is negative, we're gonna use that formula when we work on the reactants, okay?
Mm-hmm.
Right? The reactants. And the one that is positive, we're gonna use it when we work on the products. I'll definitely show you guys how this works now. So now I'm looking for the average rate in experiment 2 during, this is my delta T, and then now the first 2.5 minutes. So if this is the first 2.5 minutes, this tells you that this 2.5, it's my T final. It's my final time, and the T initial, it starts at 0. And then now we are given the average rate as what? We are given the average rate. This is my, what is this? The average rate. So this is my average rate. Average rate. Are you all with me on that?
Yes, sir.
Yes.
Okay, so now I need you guys to look at what I'm going to do from this part. Now, I'm going to say the average rate is equals to the change I'm looking for what? For aluminum carbonate. And if I go to my reaction, look at where is the aluminum carbonate. It's the reactant. So now you know which one we need to use, the one that is negative, right? 100%. So now minus, I'm going to put this on the bracket because the change in N, it tells you that the final amount, the final number of moles will minus the initial number of moles. Divide this by T final, you minus T initial. So without wasting time, this is the average rate. I think it's best. Can I take this to the other side, guys?
Yes.
Just for space, né? So we are saying that the average rate that the formula will use, it will be negative N, change in N over the change in T. And then now this is the same as saying negative into N final minus N initial. Okay, everything divided by delta T. Okay, let me Okay, so what I'm trying to do here, guys, I'm trying to say this is divided by T final minus T initial, right? So when I do the substitution, what is the average rate? If you look at that question paper, it's given as 4.4 times 10 to the power negative 3. So I'm going to substitute this and say this is 4.4 times 10 to the power minus 3 is equal to negative into the final number of moles. It's what we are looking for minus the initial. What did we start with? So we can see that they said for experiment 2, we said initially we start with what? With that 0.016. Are you all with me on that?
Yes,
Yes.
sir.
Okay, so initially we start with 0.016 and then everything is divided by T final, they said is 2.5, we minus the initial, which is 0. So when we work this thing out, we can say if we multiply the top part by negative, this will be negative. The final F plus 0.016, divide everything by 2.5. It's equals to 4.4 times 10 to the power minus 3. So now I can just multiply this side by 2.5, multiply the other side by 2.5. Therefore, what do we get when we put that on the calculator? Can someone please assist with the calculator?
Mhm.
Are you guys winning?
Wait, a few minutes. Okay, wait. Okay, for screen to the negative 3 times 2.5. Who? Okay, so I get 0.011.
Okay, so this is 0.011 like that.
Yes, when I times the
So
2.5 times the 4 times 10.
yes, and then we left with minus n final plus 0.016, right? The 0.016 will come this side. This will be 0.011. We minus the 0.016, which is equal to negative and final. So what do you get when you subtract the two? 0.005, right?
Yes.
Negative.
Yeah.
Therefore, divide both sides by that negative 1, divide by that negative 1. Therefore, n final, it's equal to 0.05. Remember, this thing is the number of moles of what? Is the number of moles of that, the change in number of moles of that aluminum carbonate. I hope you guys understand. It's just 0.005.
Yes.
Okay?
Okay.
So, guys, one thing I want to tell you now is that you guys can get different answers. It will depend on which reference are you using. You understand? Because look at the formula. We said that if we are using the reactants, we use minus, and for the product, positive. So let me give you, there's another way that we can solve this using one of the products. But now we'll get an answer that is different to that one, but it's still correct. It depends on what you use as your reference. So let's say that you tell the examiner that I'll use this carbon dioxide as my reference. You understand? So when I use carbon as reference, we can see that the carbon is product and the average rate it will be positive the change in N over delta T, okay?
Okay.
So when you do it like this, when you use the what is this? When you use, just give me a second, guys. Okay, so now I'm saying that if we use the product, we're gonna say with reference to CO2. Are you still with me?
Yes.
Yes.
Okay, so you're gonna write it down and say with reference to CO2. So now the average rate is 4.4 times 10 to the power minus 3. It's equal to change in N all over. Don't say T final, T minus is fine. You can just say 2.5 and then change in N is equals to 2.5. You multiply that by 4.4 times 10 to the power minus 3. So this tells you that the change in N is equal to what? We got 0.11, eh?
Yes. 0.011.
0.0, it's 0.1, 0.011.
Mm.
So now that you set with reference to CO2, this guy, the one that you got, it's what we call the change in N we set with reference to the carbon dioxide. So it's 0.011. But now remember the question wants the change in what? The change in aluminum carbonate, okay? So we're gonna use what we call the mole ratio. So when you use the mole ratio, this is 3 and this is 1. So the mole ratio is 1:3.
Mm.
So this tells you that the number of moles for that aluminum carbonate is to the number of moles of CO2, and this is 1:3. So if this is 1:3, this tells you that this one here, this is 0.011, and we are looking for X. We don't know what is the number of moles of that. We just have to cross multiply. This times this times that, okay? So this will be 3X, it's equals to 1 times that, this is 0.011. We are looking for X, which is the number of moles of that aluminum carbonate. Divide both sides by 3, we get X to be equals to, what do you get on your calculator?
3.67 times 10 to the negative 3.
3.6 what?
7
7
times.
times 10 to the power minus 3.
Mm.
So now, remember, we are talking about the change. Né? So since we are talking about the change, this guy that you got, it's what we call the number of moles final. That is the number of moles final, and we know what is the number of moles initially. So this tells you that the number of moles of that Al2 CO3 final will be we're gonna take what we start with initially, then you minus what's left. You understand? So we need to know what is left, because this is what we have final, and then we started with 0.016. So to find this, we're gonna take the 0.016, you minus that 3.67 times 10 to the power minus 3. I know this is the complicated way, but I prefer that we stick to the first module, to the first method. Né? The answer that you get is the number of moles for that aluminum carbonate. Guys, there's many ways that you can work around these things. You can also use another reference. You can use HCl as the reference. You can also use that AlCl3 as reference. But I think the first one, just to go straight to the point, is the easiest one.
Yeah.
The easiest one, né?
Mm.
Okay, I think, was that the last one? Was that the last question? 5.5. Calculate the maximum volume. So they want V of CO2 that can be prepared at 25 degrees Celsius in experiment 1. Take molar gas volume. Guys, molar gas volume is Vm. So for the fact that they mentioned Vm, I'll go to my formula sheet, find the formula that has Vm. Okay, so it's N is equal to V over Vm is at the back of your question page.
Yeah.
So they want us to find this Vm is given as 24,000 centimeter cube, and then this volume is what we are looking for, but we can calculate the number of moles of CO2. So that's what you need to do first. Number of moles of CO2. We're gonna use the formula. We know that the number of moles of CO2 is equals to, I'm going to use the, what is this? I'm going to use the mole ratio because I don't have the mass. I can use that M over big M. I can find the molar mass, but the mass is not given. So you just have to use the molar, the mole ratio. So look at this. We know that the reactants started with 0.016, and then we're looking for the number of moles of CO2. So the ratio is 1:3. Okay, so the ratio is 1:3, and I'm just gonna work this thing out and say the ratio is equals to 3 times what? 3 times the number of moles of that aluminum carbonate. Guys, it's very important for you to understand why I'm gonna say this is 3 into the 0.016. The number of moles of carbon dioxide. It's very important for you to know why am I using that formula? Why am I saying the number of moles of carbon will be 3 times the number of moles of aluminum carbonate initially, what we started with? Because the mole ratio is 1:3. So the mole ratio is 1:3, and this one is for the aluminum carbonate, and then is 2. This 3 is for the carbon dioxide. So if we cross multiply, this 1 times the carbon is just the carbon dioxide. So the number of moles of carbon dioxide will be equal to this times that is 3 times the number of moles of that Al2CO3. Guys, I'm very sorry about the mess, but I think you understand where I'm going with this, né? You still with me?
Yes, sir.
Okay, so now I know that the number of moles, what do you get when you punch this on the calculator? What is 3 times 0.016?
16, we get 0.048.
Okay, 0.048. And then, don't worry guys, I have a lesson for these questions already, and I can send you guys the link after the lesson to watch. Né? Don't worry, there's already a lesson. On the lesson, I'm also using different methods, so it's fine. So now this is 0.048. And then when we find this, we know that to substitute this, the number of moles, it's 0.048. It's equals to V over that 24,000. So you can see that to find V, we need to take the 0.048, multiply that by 24,000. And I'm just gonna leave it like that, né? What time is it?
3:45, sir.
3:45.
45.
So we have 15 minutes to do question 6. That's impossible.
Do we have any lessons later, sir?
I think so. Remember, you need work energy and power, right? So now I have a lesson that I need to start. grade 10, but you said you need work energy and power. So if I still have the energy, we can schedule that work energy and power.
Okay, sir.
What did you guys get when you say 0.48 times 24,000?
1152.
1152.
Mm.
Okay.
Yes, I mean.
So one thing I need you to note is that this 1152, it's in centimeter cube. You can write it in decimeter cube by dividing by 1,000, which will be 1.152 decimeter cube.
Okay.
If you convert it into decimeter cube, or you can just leave it like that.
Okay.
Do you guys have any question on that?
No, sir.
Okay, let's look at question 6. Define the term chemical equilibrium. What is chemical equilibrium? We know that chemical equilibrium is a stage in chemical reaction. It's a stage
Action where the system tries to oppose.
Chemical reaction when the rate of the forward reaction and the reverse reaction. Okay, the forward reaction and the reverse reaction is the, okay, let's just say are equal, ne?
Mm-hmm.
So the stage in chemical, there's someone saying something.
No, sir.
Look this, ne? Look at this. I know that we are saying that the rate of the forward reaction and the reverse reaction are equal. And if you use the concentration, if you define using the concentration of reactants and products, okay?
Mm-hmm.
Don't say equal. They remain constant.
Yeah.
They are not equal, but they remain constant. Ne?
Yeah.
You agree with me?
Yeah, boy.
Okay. The graph below shows how the concentration of the reactants and products vary with time during an investigation, and we can see that which one of the curves, X or Y, represent the changes in the concentration of the products. Guys, look at this. Which graph represents the concentration of the product? I want to see something. Can someone try to give me an answer?
What is which? Let me read the question. Which graph X or Y represents the? So the. Should I answer, sir?
Yes, please.
Okay. So I'm gonna say that the X is the reverse, and then the Y is the forward.
Okay, no, I don't want you to give it to me as the reverse and the product. Just tell me between X and Y, which one represent the changes in concentration of the products.
The changes in concentration.
Yes, and think about this. You'll see that it's easy for you to take that 2 marks. Think about it.
Which
Product.
one of the curves represent the changes?
Okay, you want me to give you a clue.
Mm.
When we calculate KC and we use the Rice table method, the initial number of moles on products, what do we do? What do we put on the initial number of moles?
We put the number of moles that we calculated.
No, listen, when we do the Rice table method, the number of moles that we put on the rice table. What do we put for products?
Oh,
Initially, what does we put?
0.
0.
For products.
So now tell me. Now that's correct. We put 0. Now tell me which graph represents the concentration of the products.
X.
Exactly. Why?
Because it begins at 0.
Thank you very much. That's how you collect that 2 marks.
Yeah.
So we're going to say the correct one is X. The reason the graph starts at
0.
0. So you can say it's X because no products
I mean, in the beginning.
were initially present.
Yeah.
You can look at this. So in order for you to know which ones are your reactants, which one are your products, which one represent the concentration of the reactants, which one represent the concentration of the product. Just know that the products will always start at 0. So this one will be, it represent the concentration of the products. Okay, and that one, the reason is 0. Or look at this. Another way to say this, Emihle, is that the concentration of the products are increasing. Because remember, in a chemical reaction, we used up the reactants to form what? Products. So you can see that the concentration of the products are increasing.
Yeah, I remember.
Another way to say, you can say that the concentration of the reactants are decreasing, because this is why it's decreasing. You see,
it's being used up. Yeah, I get it.
And then, how does the rate of the forward reaction compare to that of the reverse reaction at T4? So if you look at T4, this is my T4 here. Okay, so this is my T4. How is the rate of forward compared to that of the reverse reaction? Are they equal, lower than, or higher than?
Equal.
The rate of reaction. How does the rate of the forward reaction compare to that of the reverse reaction? Look at this, guys. When it's like this, look at this. The forward reaction, which one is the forward reaction? Which one is the reverse reaction?
Y is forward, X is the reverse.
X is the reverse. Are you sure? Are you sure? Look at this. If the concentration are decreasing, this tells you that this is what the concentration are decreasing. This is the forward. Thank you very much. And then this will be my
reverse.
What are we saying? Reverse, né? So now they are asking us, how does the rate of the forward reaction compare to that of the reverse reaction at T4? So at T4, we look that no, I'm sorry, this won't be the forward reaction. The forward reaction is where we produce the products. So X will be the forward reaction, okay?
Okay.
This is the forward, this is the reverse. Why? Because we are producing products. The forward reaction is the one that gives us the product, okay? The reverse reaction is the one that increases the reactants. So when I look at this, the products are increasing. So the one that increases the product is the forward. So X is the one that is forward. Now, to answer this question, I'm going to say at T4, the system has not reached equilibrium, right? So since it has not reached equilibrium, we can see that the concentration of the products are what? The concentration of the product are still increasing. So this tells you that the forward reaction is higher than the reverse. The forward reaction is happening faster than the reverse. So the correct answer is higher than. Are you happy with that?
Yes.
Yeah.
Okay. Don't worry, Johan, I'm still going to cook you. Don't worry, you'll be ready for your exam. So now, let's look at this 9 marks. Do we have enough time to work on that 9 marks?
We have 5 minutes.
5 minutes, then I'm just gonna work it out and leave you guys to complete it on your own. Né?
Okay.
Okay, sir.
So please use what we call the rice method. Did you eat rice today, Emily?
No, I didn't.
What did you eat, Johan?
I did eat rice today, sir.
Rice, ne? Right. I hope you're going to understand this much better because you have rice in your system. So now, the rice table method, this is how it works, ne? So first thing first, we're gonna talk about the first block, and then let's look at the equation. We have the reactants and then the products, okay? So the first block will be it will be HI. So the first block, which will be here, I'm gonna put HI, then this will be my, let's see what we have, hydrogen and iodine. So this one will be hydrogen, which is H2, and this one will be L2. So now with this, first thing first, the first row is for the ratio. So if the first row is for the ratio, look at that graph. What's wrong? What's wrong? What's wrong? So the ratio is 2:1:1. Let's go and write that. I hope you understand. Did you guys see what I did? 2:1:1. Are you all happy with that?
Mm-hmm.
Yes, sir.
Okay. Then the next column, I stands for initially. Initially, you need to write down the number of moles that you start with. We need to read the statement. They said that pure hydrogen of HI, and it has the concentration of 1 in a sealed 500 centimeter container. So initially, HI starts with the concentration of 1 and the volume is 0.5. So we can use that information to calculate the number of moles initially. Because remember, C is equal to N over V. Therefore, the number of moles will be the concentration times the volume. The concentration there is given as 1. This is the concentration. It's given as 1 multiplied by the volume, converted by dividing that by 1,000, which is 0.5. So this will be 0.5 times 1. So initially, HI will start with 0.5. So if you punch this on the calculator, get that. Initially, we start with 0.5 for HI. You understand?
Mm.
And remember, we said that the number of moles for products, they start with 0. So this will be 0. Okay? So now the next column, you look at the ratio. The ratio is 1. We are looking for the number of moles. They say Kc for the reaction is 0.4. And then calculate the number of moles. If you are looking for the number of moles, you take your ratios, you multiply them by x. It's 1 times x, that's x. 1 times x, that's x. 2 times x, that's 2x. That's what you do. You only do this if you are looking for the number of moles. Then the next part is the number of moles at equilibrium, which also plays a very important part in your calculations. The number of moles at equilibrium. The first one, we start with 0, then we end with the change is x. So this tells you that at the end, we'll have x as the number of moles. We start with 0, we gain x. At the end, the reaction will end with x. But this one, we start with 0.5. We use 2x. So to know that what we have at equilibrium, we take the 0.25, we minus the change, whatever that we used, to know the number of moles at equilibrium. Are you all with me on that?
Yes, sir.
Yes, sir.
Okay. Then the last one, this block here, it shows you that you calculate the concentration. And if you still remember, C is equal to the number of moles at equilibrium over the volume. The volume we set is 0.5 because it was given as 500 centimeter cube. We converted that, divided that by 1000 to get 0.5.
Yeah.
That's the number of moles. That's the volume. So look at this. At equilibrium, we have X. So the number of moles, it's X, and the volume is 0.5. So for this one, it will be X over 0.5. That's the concentration. So we also have to find the concentration for, remember, this is the concentration for L2. We need to find the concentration for H2, which will be the number of moles, it's X over 0.5. So this will be X over 0.5. And then the last one is the concentration of HI. This is equals to the number of moles at equilibrium, 0.25 minus 2x, everything divided by 0.5. So this will be 0.25 minus 2x, everything divided by 0.5. Then the question said the number of moles of iodine at equilibrium is this X. This is the X that you are looking for. So you're going to use the Kc and say that Kc is the concentration of the products
Over the concentration.
times that, and then divide by the concentration of the reactants. So the concentration of the reactants, if we check, this was 2, 1, and 1. So this is to the power 1, this is to the power 1, and then this will be to the power 2. We take those ratios, we square them, or we put them on top. Kc is given as 0.4, 0.04. H2, look at what we have on H2. 0. It's X over 0.5. We need to take that, multiply with X over 0.5, and then everything is divided by what? Everything is divided by the 0.25 minus 2x over 0.5, and everything here is squared. So now remember, to find the number of moles, we just have to solve for X on that expression. So so far, look at this. Everything that we did, we have how many marks? 8 marks. Right? The only 1 mark left is for you to find X. So that's your task. Go and apply the algebra. Let's see if you can manage to find your X. So when you solve that, X should be equals to 0.071 mole. Guys, try and see if you can solve this complicated expression. I want to see if you guys still remember how to work around your algebra.
Okay, sir.
Okay, sir.
Okay? Yeah, please try and go and work on that. I'll definitely send this PDF. Then you guys will try to work on it. Okay?
Okay, sir.
Okay, guys, I need to run to the other lesson. This is where we're gonna stop. And I'm
Okay.
looking forward to our next lesson where we'll do electrochemistry and acids and base.
Okay, sir. Bye. Thank you.
Okay, bye, sir.
Sharp, sharp. At equilibrium, which is X. So we are looking for that X. If we can find X, we'll know what is the number of moles. So now I see that we don't have much space. So I'm just gonna take this and write it on the other side, then we can work on that. Okay, so when you see this type of questions, you don't have to panic and feel like whatever that you are doing is wrong. Just follow the steps to solve this. First thing first, I'm gonna leave the 0.04 that side. Then I'm gonna row multiply these two guys. X times X, then I need to say 0.5 times 0.5. I know that X times X, that's X squared. Everything divided by, I need to take the 0.5, multiply that with 0.5. Okay, so this gives us 0.25. So I'm going to write 0.25 down there. and then this, everything is divided by. Okay, so you know, when I have this type of questions, you know what I'm gonna do? I'm gonna leave the top part to be squared. Okay, I'm gonna remember, if I have a over b and everything squared, we can write this as a squared over b squared. So now I can say this is 0.5 minus 2x, square the numerator, then we also have to square 0.5. Okay, so 0.5 squared. So I know that we just set 0.5 times 0.5, which is 0.25. So I'm not gonna waste any time. I know this is 0.25. So instead of writing 0.5 squared, I'll write this as 0.25. So look at this. This is the main division, and we are dividing two fractions. We can write this in this form. We can say this is 0.04. It's equals to x squared over 0.25. Instead of division, we can multiply by the reciprocal, meaning that the denominator becomes our numerator, and then the numerator becomes our denominator, which is 0.5 minus 2x, everything squared. So now I think you can see that the 0.25 will cancel. And what do we have now? This will leave you with the 0.04. It's equals to, this is 1, and then we are left with 1 there. X times 1, x squared times 1, that's x squared over 0.5 minus 2x, which is also squared. Look at this. The numerator and the denominator, both of them are squared. We can write this in this form. 0.04. Then remember, if I have a squared over b squared, I can revise the law and say this is a over b, everything squared. So I'm just going to write this as x over 0.5 minus 2x, then everything squared. So the reason I'm doing this is that I don't want to, you see, someone here will just expand the bracket, multiply out the, please don't do that, because we're going to make the equation, the whatever that we're working on, to be more complicated. Okay, so now I can just square both sides to get rid of that square. So I can square both sides. I know that if I put that on the calculator, what is the square root of 0.04? 0.04, the square root of that, that's 0.0 or 0.2. Okay, so if it's 0.2, this tells me that I'll have 0.2, which is equated to just x over 0.5 minus 2x. You don't have to show all this on your workings. Just do this on your question paper, give them the answer, definitely get all the marks, because in most cases, there's no mark for all the steps that you are doing. But in order for you to know the number of moles, you need to do the steps. So when it's like this, I know this is over 1. I can cross multiply and take the 0.2, multiply that by 0.5 minus 2x, equate that to x. So let's multiply out the bracket by that 0.2. So I'll have 0.2 multiplied by 0.5. That gives us 0.1. So this will be 0.1. Then we need to take the 0.2, multiply it by -2. 0.2, multiply that guy by -2. Okay, this gives us -0.4. So this will be -0.4x, which is equals to x. So from this part, I need to group the like terms. The one with x has to come this side, which is 0.1. Oh, okay. I'm not sure. Did we get the answer 0.1 when we set 0.2? I just want to confirm this. 0.5. This is 0.1. Okay. So now this will be x. We add the 0.4x, because when it goes to the other side, it will definitely be positive. So let's add 1. Remember, x is just 1x. So when we add these two, it should be 1 plus 0.4. So this will be 1 plus 0.4, which gives us an answer of 1.4. So 0.1, it's equal to 1.4x. Divide both sides by that 1.4. Divide both sides by 1.4. Therefore, when you calculate, what do you get? What is your x equals to? So this will be 0.1 divided by answer. This gives us an answer of 0.071. Please just avoid that one on top. It just tells you that those numbers are repeating or something, but just write the 0. Let me try to clear my calculator and see what happens. Answer. Okay, so I'm just gonna write 0.071. 0.071 is our answer. So x is equal to 0.071. So these are the number of moles of iodine at equilibrium. So what I'm gonna do, I'll just go back to my workings, and I'm just gonna say when you have it like this, guys, please trust me when I say there are no marks for all those steps that we did. You just have to, from this point, you're gonna say therefore x is equal to 0.071. Yes, I know life is not fair, né? 0.71 mole. Imagine all the work that we did, but still we don't have any marks for that. It's fine. It's fine. We need that 1 mark, so I'll definitely go through all the trouble to get that 1 mark. Okay, so and that's it for this question. This is how you answer question 9. Wow. You see, now I'm saying this is question 9. It's not question 9, it's question 3. My focus is on that 9 mark. That's how greedy I am when it comes to marks. Okay, so now on 6.4 they say the graph below shows how the rate of the forward and the reversing changes with time. And now we can see that the straight one is the forward, and the one that is the solid line is the reverse reaction. So now they say that the temperature of the container is increased at T10. So at T10, this is where you increase the concentration. Okay, so and they are asking that which reaction shows an increase in rate at, guys, please underline the keyword, very important, rate. We are not talking about they want us to understand which reaction shows an increase in rate at T10. Choose forward, reverse, both forward and reverse. Guys, remember that when you increase the temperature, which one will be affected? So if you can look at this point, we increase the temperature. And if you still remember, on our previous lessons on the other channel, we talked about that the increase in temperature will affect both the forward and the reverse reaction. As you can see from the graph, both of them, they shift. If you can look at the graph, this one shifts to this point, then this one shifts to that point. So both of them, they shift. So what I can say is that at T10, the temperature increase. This cause both the forward reaction to increase immediately, because remember, the particles, they gain energy, leading to move what? To more frequent effective collision. I hope you guys understand that. Né? So at T10, maybe in an exam, they can also ask you to find the, look at this. We are saying that the answer is both the forward and the reverse. Right. So the reason, I'm not sure if we should just put the reason down on the board, but please note that when the temperatures increase at that T10, both the reaction increase immediately because the particle, gain energy, leading to what? To more frequent effective collision. So the last question they ask you is the heat of the reaction for this reaction positive or negative? Fully explain your answer in that format. So you know what I'm gonna give them? I'm just gonna first look at this problem, try to analyze it. So we are saying that at T10, both rates increase due to high temperature. So at T10, okay, at T10, we can see that both the reaction, they increase. Why are the reaction increasing? Because of the temperature increased. Okay, so from that, we know that if the temperature is increased, an increase in temperature favors what? If the temperature is increased, we're gonna favor endothermic. Thermic reaction, endothermic reaction. So now, if the temperature is decreased, we favor exothermic reaction. Okay, so this tells you that looking at this reaction, you can see that the forward reaction, the rate of the forward reaction becomes greater than the reverse. So from this, we can see that the rate of forward reaction becomes greater than, okay, greater than of the reverse. Okay, what can we conclude about that information? This only happens after the temperature it's increased. Okay, so after the temperature increased, the rate of the forward reaction becomes greater than, guys, what I'm giving you now is already I'm answering this when they say fully explain your answer. I'm already working on fully explaining my answer. So now, first thing first, we said that at T10, both the reaction increased because the temperature increased. Then the endothermic reaction favors the increase in temperature. So now I'm telling you that the rate of the forward reaction becomes greater than what? Than the reverse because of the increase in temperature. So now we can say that the system adjusts until the new equilibrium is reached. Okay, so the system will adjust until the new equilibrium is reached. And to put this thing in simple form is that an increase in temperature will favor the forward reaction. What? So now you can see that if the forward reaction is favored, what happens? It's endothermic, right? The forward reaction will be endothermic because heat must act as a reactant. So the heat, it must act as the reactants, right? The heat must act as the reactants in the forward direction. If this does not make sense, please try to pause the lesson, think about it, okay? Therefore, since the heat must act as the reactant, this tells you that we can conclude and say that our change in enthalpy, delta H, is greater than 0. Okay, so the forward, if delta H is greater than 0, this tells you that the forward absorbs the heat. So the forward absorbs the heat. So since it absorbs the heat, the endothermic reaction is favored. So to answer your question, delta H is positive. The delta H is positive because we said the forward absorbs the heat. Okay, I hope you guys understand, but let me put this in simple terms for you to understand all the information that I have there. I'm just gonna put it in simple way for you to understand so that you can stay on the lesson and think about this. Now, we said that delta H, okay, delta H is greater than 0 positive. The reason is that the forward reaction is favored. Right. When I look at this, the reason that we see that the forward reaction is favored is the one that is, if you can look at this, the forward reaction is the one that is greater than the reverse. The one that is greater is the one that is favored. So the forward reaction is favored. Right. Then what can we say about that? Temperature increased. This favors what? This favors endothermic. So this tells you that the forward reaction is endothermic. And if the forward reaction is endothermic, therefore, you can just say that the forward, it's endothermic. So this tells you that we can go back to that. Let's say, let me see. For example, if I give you something like this here, I'll say delta H is greater than 0. This tells you that the forward is endothermic. So that's how we got the answer. So this is the simplest way to explain this, okay? So delta H is greater than 0 because the forward reaction is favored and increasing temperature favors endothermic. Therefore, we can conclude and say forward is endothermic. I hope you guys understand that part, and I hope you guys had so much fun working with me on this lesson. If you really enjoyed the lesson, I'm looking forward to see you on the upcoming lesson where we'll be working on question 7, which has to do with acids and base. So if this is your first time watching the lesson, please don't forget to subscribe, join the family, and we'll make sure that you feel at home.